Acorn includes a coordinate decomposition, a coordinate encoder, and a coordinate decoder. In the coordinate decomposition, they apply a multi-scale block partitions to the input space according to the local signal complexity. That is to say, they apply more intense blocks to the highly textured regions and apply coarser blocks to flat textured regions, like the regions in the same color. And they have a two-stage network architecture, which consists of a coordinate encoder and a coordinate decoder that map input spatial and scale coordinates to an output signal. In each block, they have global indices and local indices. In the coordinate decoder, they map a global block index to a grid of features, so that a grid vector can be extracted by a bilinear for 2D or a trilinear for 3D interpolations. And in the feature decoder, they map the feature vector to the output signal, so that the output of decoder approximates the signal of interest at the global coordinate x. The encoder network, they have 4 hidden layers with 512 units in each layer. This part is the most expensive part in the whole algorithm. But we only need one forward pass in each iteration. In the decoder network, they have 1 hidden layer with 64 units. So before running the code, we have to set up some environments it needs. The most important one is the Groby. It uses the Groby packages to solve the ILP optimization problem. We can use this command to run a 2D task of Plato acorn in 1K resolution. If you change the experiment name, you can run different 2D tasks. Model. To train 3D models, firstly, we should download the dataset from the Stanford 3D repository. So this is the main function for training 2D images. Here are some training parameters: the learning rate, the number of iterations to train for, and some storage settings. Firstly, we should specify the dataset. Here it provides several dataset choices. I only use the Plato dataset. Here are the model options. The patch size is used in the coordinate decomposition. And the hidden features, the hidden layers, is for the encoder network. And this is for comparison of acorn and siren model. Update the decomposition partition every 500 steps. And this is the MV parameter, i.e. the maximum number of blocks in the optimization. The coordinate dataset uses a function in data input and output file. And the number of epochs for the whole algorithm is related to the iterations and the dataset size. And we specify the image resolution here. If the model type is acorn, here is a network definition functions in the module file. Also, they print the number of model parameters when using the code. And during the optimization, they use the mean square estimation function for calculate the loss. For output, they calculate loss every 100 steps. The pruning is used to frozen some uniform blocks. And this is for resuming from a safe checkpoint. And here, in this function, they evaluate the peak signal to noise ratio and save them training images. And here is an option for uniform samples without the multi-scale partition for the input space. Here, calculate and record the matrix. They use peak signal to noise ratio and structural similarity to evaluate the output. Also, they save the training images and the ground truth images. The output of decomposition is saved every 100 steps. So this is the main function. In the training procedure, it's shown in the paper like this for every block in the global coordinates. we can calculate the block error and update the weights in the optimization problem. And if the iteration is equal, and in every 5 steps of iteration, we optimize the partition block sets. And if in every pruning steps, we prune the partition blocks by frozen the uniform blocks. And we repeat the whole procedure for number of iterations we give. In the module file, we define a positional encoding function. This is between the coordinate decomposition and the coordinate encoder. And we also define the neural networks and their forward paths. Structure file, we define a quad tree class for 2D image tasks. And we define a class of patch to make decisions for staying, merging, or splitting of blocks. And we define a walk tree for the 3D models. After the training, the output file will be saved in the logs file, named as the training task. Like in the Plato acorn in 1K resolution, we have the checkpoint files. We can see the whole losses for the iterations. In the eval file, we have the ground truth images. And we also have the training images in every 100 steps. The tiling is the output of the decomposition partition. And also the model information of the encoder and decoder is saved here. Besides, they will save a configuration file for the whole model. Here, the experiment is the Plato acorn in 1K resolution. This is the 1K resolution, and in every 500 steps, we update the decomposition. Another trial is to train a model for Thai statue. This is a very in-dense polygonal model, and the dataset comes from the Stanford 3D repository. Smaller blocks tend to be concentrated in the highly textured regions, and the flat textured regions tend to be coarsely divided. Also, a final mesh can be exported once the training completes. And during the training and after the training, we can also see all the outputs from the tensor board by choosing the task name. We can see the image loss and 3D model loss. And we can see the ground truth and prediction images. And we can see the peak signal to noise ratio and the decomposition mesh.